Alright, back again. Let's look at another example about finding eigenvalues and eigenvectors and building a general solution to a system of two differential equations, two unknown functions. Alright, we're talking about linear system here, constant coefficients. So let's keep sight of the fact that our coefficient matrix is related to the coefficients of x and y in the system. Alright, I've got the system written over to the right side there. But again, there's no y in the first equation, so of course the coefficient is 0 there. There's no coefficient in front of x in the second equation, so that coefficient is 1. So we can see those numbers 3, 0, 1, and -2 in our coefficient matrix. Alright, now let's go through our steps like we've seen in our previous recordings for this matrix here. So first thing we do is write down A minus lambda times the identity matrix. And we're getting a little faster at this now, hopefully, or a little more comfortable with it. So we write down our matrix A minus the matrix that has lambda down the main diagonals in zeros and the off diagonal, because the identity matrix has 1s down the main diagonals and zeros everywhere else. If we multiply every entry in the matrix by lambda, 0 times anything is 0, 1 times anything is that number, and that's the resulting matrix we get. So now what we end up doing is 3 minus lambda, 0, 1, and then -2 minus lambda. Subtract entry by entry or component by component in your matrix. So really what we're doing when we form that matrix is just subtracting lambda down the main diagonal of the matrix A. Everything else stays the same. The 0 and the 1 are the same. It's just 3 minus lambda, -2 minus lambda. Then we take the determinant of that matrix and set it equals 0 and solve the resulting polynomial equation. That is always going to give us our eigenvalues. Right, that will never change in the rest of chapter 3 here. Alright, so what are we going to get in this case? We're going to get 3 minus lambda times -2 minus lambda minus 1 times 0. Okay, well 1 times 0 is 0, so that term just wipes out. We can multiply that out. Okay, and I will do that, but I'll make a comment about that in a minute. If we multiply this out, we would get -6 plus, minus 3 lambda plus 2 lambda plus lambda squared. And from there, we got to go through and solve or combine like terms, and then we'll solve that resulting equation. So now let's rewrite that in descending order. So we get lambda squared minus 1 lambda and then -6. Okay, but that factors as lambda minus, well, let's do plus 2 first, and then lambda minus 3 second. Okay, but just notice one thing up here. If we would have factored a negative out of both of the factors up above, which I'll just underline temporarily, then we would have ended up with these exact same polynomial factors. So because that the term that we're subtracting off came out to 0, we could have just solved this by factoring, by setting both of those equal 0, and would have obtained the same result. Okay, now again what we're going to do is set that equal 0 and then solve that resulting equation. So when we set that equal 0, we're going to then set each factor to 0 and solve. Again, you can use the quadratic formula here too. Not that that's wrong. We get two solutions. One of them is positive, one of them is negative. We get -2 and +3 here. Okay, and like we've done before, we're going to call the smaller of the two lambda 1 and the larger of the two lambda 2. That's just my personal preference. In some of the homework in Lumen, you might need to do it in a certain order, though, so pay attention to that. Okay, now we need to find our associated eigenvectors. All right, so what are we looking for? We're looking for a vector, v1, which we have to figure out, so we're going to call it just a generic vector xy, so that a times the vector v1 is going to equal lambda 1 times the vector v1. Okay, but then putting in what the matrix is, which is 3, 0, 1, -2 times the generic vector xy, v1, then we get times -2 times xy. All right, I'm going to skip right to the system step. If we multiplied out the left and the right hand sides and then set the first component equal to the first component, the first equation the first components would be 3x and negative 2x on the left and the right sides respectively. The second components would be x minus 2y and negative 2y respectively. Okay, now this example showcases something different, but we still end up with a system that has infinitely many solutions. In fact, the whole straight line of solutions. It just manifests itself in a little different way than it did in our previous couple of examples. Because what does the first equation tell us? If you add 2x to both sides, we get 5x equals 0, which tells us what? That tells us x is equal 0. Okay, so we're stuck. X is equal to 0. Our x component of our eigenvector is 0. That's okay. All right, that's possible. All right, I'll talk about that, what that means geometrically in a minute. Now, if we take that and plug it into the second equation, that's going to give us negative 2y equals negative 2y. And that equation's always true. All right, this is true for any y. All right, well, remember what our goal is here. We have to write down a non-zero eigenvector. Well, our x component is equal to 0. If we want to write a non-zero eigenvector down, we have to pick some number for y that's not 0. So let's just take y equals 1, for instance, and that'll work. So what is our eigenvector here? What is a eigenvector, we should say? 0, 1 is 1. That would work. There's other ones. You could pick y to be 2 or 5 or 17 or negative 86. It doesn't matter. Just don't choose y equals 0. Okay, let's just talk about this graphically off to the side a little bit. If we think about this in the xy plane, saying that y or x is equal to 0 means you're talking about a point on the y-axis. So as long as you pick one of these vectors or points on the y-axis, we're in good shape. We have a non-zero eigenvector. I chose 1 or 0. I chose y to be 1, so we get the eigenvector 0, 1. Okay, like we did in the last video, what is this telling us? Our eigenvalue was negative 2. This is telling us we have a straight line solution. I'm going to call that capital Y1, which is e to the lambda 1t times v1. We derived that in a recording recently. And now we're just going to put our numbers in. We get e to the negative 2t times the eigenvector we just wrote down, which is 0, 1. So there's a solution to the system, and moreover, its graph lies on a straight line. Turns out the straight line that this lies on is the y-axis. Okay, there's that one, so that's half of it. Now we got to do the same thing for lambda 2, which was 3 in our example. So we have to find a non-zero eigenvector v2 that satisfies the matrix A times that vector v2 has got to equal our eigenvalue, which is 3, times that vector v2. Okay, and I'm going to fast forward to the system that we're going to end up with, but it's the same as we had in the previous case, in the previous part here with lambda 1. We're going to get this system, 3x is the first equation on the left side, and then x minus 2y is the second left-hand side, and that's going to equal 3 times the first component, which is x, that'll be 3x, and then 3 times the second component of v2, which is y, so 3y. Alright, so get a similar looking system, a little different, and once again, these types of systems that we're going to come across are always going to yield an infinite number of solutions. How we end up getting that conclusion can look different on a case-by-case basis. What does the first equation tell us? 3x equals 3x. This is telling us, well, nothing really. This is saying x can be anything. So that's no restriction. That does not restrict us whatsoever. It doesn't tell us anything. We need to focus our attention more on the second equation here. If we add 2y to both sides to get the y terms together, we get the equation that x is equal to 5y. So one way or another, we're going to be led to a conclusion about the components of the eigenvector that we're trying to determine. In this case, right, we don't get the system. We don't get a system where both equations in the system yield the same resulting thing. All right, the first one says nothing really for us, no restriction. The second one says a relationship between the components. Now, since x is isolated for in terms of y, we should now choose a y value, and let's choose any y value we want to except 1. Just to make our numbers easy, let's choose y equal 1. If we do that, x is going to equal 5 times 1, which is 5. So what is our corresponding eigenvector in this case? We chose y to be 1, and that resulted in the x component of that being 5. All right. So every time that's going to lead to a system with infinitely many solutions, how that kind of steers us to find the eigenvectors, all right, with the relationship between the components does vary, as we're seeing in the examples we're doing in this video, and some of the other ones that we've done. All right, now we write our straight line solution down. y2 of t is going to be e to the 3t times the eigenvector we just computed, which was the eigenvector associated to the eigenvalue lambda 2 equals 3. Okay, then once again we're going to build our general solution up. All right, and my general solution will look different than your general solution if you choose different eigenvectors than I've chosen. There's not a unique answer to this general solution, so we should say it's a general solution. What's it going to look like? It's going to be a scalar multiple of the first solution we found, plus a scalar multiple of the second solution we found. All right, so just putting those in for this example, we get k1 times, what did we have? E to the negative 2t, and then we had 0, 1 was the eigenvector. Plus k2 times k2 some arbitrary constant, and then e to the 3t times 5, 1. And there we go. That is a general solution to the system for this example. If we were given an initial condition, then we could enforce the initial conditions to find k1 and k2, and then have a vector valued function which we could graph in the phase plane or graph the components of.